Imagine the first spacecraft ever sent to another star. Not a giant ship, not a crew, a tiny probe pushed to a speed no human machine has ever reached, crossing the dark space for more than 20 years until the light of Alpha Centauri finally grows ahead of it. From Earth, that would sound like a rival. A craft has crossed 4 light years. It has reached another star. It is inside a system no human object has ever touched before. But then the reality kicks in. The probe is still moving at a mind-blowing speed, a fifth of the speed of light. It cannot simply enter orbit, slow down beside a planet, wait, turn back, look again, or settle into the system it spent decades trying to reach. The stars, the planets, the dust, the whole destination, all slide past in what feels like an instant. The onboard measurement instruments, cameras, sensors, and others get only one chance. Whatever they miss is gone forever. And by the time those monitoring it from Earth know what happened, the probe is already gone, far beyond the system, moving into the dark space on the other side. That is the uncomfortable reality of the first real interstellar mission concept. Getting to another star may be possible, but arriving there may not. Because speed solves one problem and creates another. The faster the craft goes, the sooner it reaches the destination. But the same speed that makes the journey possible also makes stopping almost impossible. So the question is not only whether we can build a machine fast enough to reach Alpha Centauri, it is also what it can do when it finally gets there. By the end of this video, you will understand why the first journey to another star may be less like an arrival than we imagine, and why crossing the distance is only the first hard step toward reaching worlds beyond our solar system. If you enjoy exploring questions like this with me, subscribing to the channel helps others find them too. Liking and sharing the video helps even more. Let's begin. Hold that small craft in your mind. It is the size of a postage stamp, with a thin metallic sail unfurled behind it, and it is moving at roughly 1/5 the speed of light. That is the most concrete near-term interstellar mission concept scientists have come up with to date. The breakthrough Starshot project, in its public reference architecture, describes exactly this craft. Gram-scale payload, square-meter sail, accelerated by a ground-based laser array, sent on a roughly 20-year crossing to Alpha Centauri to take pictures and beam them home. The mission's own project page does not describe a craft that goes into orbit at the destination. It describes a craft that takes pictures during a flyby and then sails on. That detail is easy to miss. 20 years to another star sounds like a destination. But at 20% the speed of light, the entire Alpha Centauri system is something the craft passes through in a window measured in hours, and the published numbers from René Helle and Michael Hipke are very blunt about it. A photon sail, moving at 1/5 the speed of light, crosses the inner part of the system in hours, not days, and certainly not in any time long enough to settle into any kind of stable observing perch. The encounter is a tear-through. Every science return has to happen inside that narrow geometric pass, so already a strange split appears. The thing the public imagines as the first arrival at another star is, in the working version of the only concrete fast architecture available, a flyby. The mission is designed to win the crossing. It is not designed to do anything that resembles arrival in the ordinary meaning of that word. The mission is honest about this. The architecture chose it. The science the mission can do flows from that choice. It is worth saying out loud what that means for the mission. Think about a planetary flyby in our own system, like Voyager passing Saturn or New Horizons passing Pluto. Those encounters were already extraordinary efforts in compressed observing, with cameras, spectrometers, and magnetometers all running at once during a few hours of closest approach. New Horizons spent 9 years getting to Pluto, and then performed its main science in roughly 24 hours. The data was stored on board and downloaded over months. That worked because the next nearest planet was still close enough that the radio signal could carry the data home at usable rates, and because the mission planners knew exactly when the science window opened and closed. Take the same idea and move it to Alpha Centauri at relativistic speed, and the geometry hardens. The craft is over 4 light-years away. The transmitter is gram scale. The receiver array back at the solar system is, in any honest architecture, a large but not unbounded set of stations. Every bit of data has to travel 4 years just to begin to be heard, and the science window is no longer 24 hours of careful Voyager-style observing. It is the inside of a relativistic pass through a star system. The instruments either work in that window or they do not work at all, and the team back on Earth will not learn the answer for another 4 years. That is the difference between arrival and flyby, written in mission terms rather than in feeling. An arrival is a state the mission settles into. A flyby is a state the mission survives. An arrival lets the team retarget the camera, recheck the magnetometer reading, and ask the spacecraft to look at the second planet after it finishes looking at the first. A flyby grants none of that. The mission has one chance in a window the physics chose, and the results are whatever the instruments happen to catch. You can also feel the split in the observer's seat. The team on Earth sees the science come back as one tightly bound packet, taken at one moment, with no opportunity to ask follow-up questions of the craft. Not because the science team is not curious, because the craft is on the other side of the system, still moving at relativistic speed, with no engine to bring it back. The mission has spent its arrival the moment it began the crossing. There is one more thing worth holding in this opening picture. 20 years sounds like a fair price for the first interstellar mission. But 20 years pays only for the crossing. The mission that comes out at the other end is the kind that takes a single sweeping picture of another world, beams it home, and continues into the dark. The kind of mission that could sit at Alpha Centauri and study it the way humans have studied Saturn or Mars is not the same mission. It is built around a different bargain. So if we are willing to call this the first arrival at another star, we should at least be honest about what arrival has come to mean in this case. There is also a useful comparison with our own past. A Voyager-class mission to Saturn took a Saturnian moon system that was almost entirely unknown and turned it into a place humans now recognize. The Cassini mission then turned it into a place we have studied. 2 missions, different architectures, different timelines, different kinds of answers. The first was the visit, the second was the residence. Each one was scientifically essential. The Voyager flyby, on its own, would not have answered the questions the orbital mission ended up answering. Cassini, by itself, would never have happened if Voyager had not first shown what was worth investigating. The Voyager-Cassini sequence is not a story about a failed first mission. It is a story about how the first mission's role is to make the second mission's job possible. The interstellar flyby has the same shape. So a thoughtful first interstellar mission is not less than the resident mission. It is a different role in a longer program. The first crossing takes the pictures, gathers the field measurements, returns the data, and shows the rest of the field where the harder problems actually live. The arrival mission, if it comes, builds on what the flyby learned. It also matters that the public conversation about breakthrough starshot already reflects this split, even when it does not name it. People who follow the project closely talk about light years and laser arrays and 20-year crossings. People who think a little harder ask, almost immediately, whether the probe is going to stop. The answer, on the project's own pages, is that it is not. It is going to take pictures and continue. The public language and the project language are saying the same thing in different words. The project says flyby. The public says the probe will not stop. Those are not different statements. They're the same statement seen from 2 sides of a translation layer. There is a corresponding answer beginning to take shape in mission planning groups. If the first crossing is going to be a flyby, then the entire science program for that crossing has to be designed around the few hours the geometry allows. The instruments have to be chosen for what they can capture in that window. The encounter trajectory has to be sized for what the team can plan 2 decades in advance. The downlink budget has to be allocated for a transmitter operating in increasingly distant geometry, sending a small but valuable data set over a span of years. Each one of those decisions reinforces the same realization. The mission is not arriving in any normal sense. It is performing a measurement event, then continuing into deeper interstellar space. And the only access we get to its result is whatever the cameras and antennas captured during that brief pass. That is also why the title is in this particular form. It is not that no human craft will ever stop at another star. It is that the first realistic concept on anyone's near-term roadmap does not stop. And the reasons it does not stop are the same reasons it can reach in the first place. There is a structural connection between speed and not stopping in this architecture, and the rest of the argument lives inside that connection, where it sits in the design, what tries to break it, and why the attempts fall short of restoring an arrival mission within anything resembling Starshot's timeframes. If the craft cannot stay, then getting there has not yet become arrival. That is the question the rest of tonight has to take seriously. Step back to the launch pad, or to the launch concept, because there is no pad in this story. The reason a fast interstellar mission exists at all is not stronger rockets. It is a different idea about where the energy lives. In Philip Lubin's directed energy roadmap, the spacecraft itself is tiny. The energy is not on board. The energy is back at the solar system, in a phased laser array that pushes the sail from behind for a few minutes of intense thrust. After that brief shove, the craft is on its own ballistic path for the next 20 or so years. The engine, in the ordinary sense, is left at home. That is the bargain that opens up the entire interstellar story for serious physics. Once you stop carrying the power source, the rocket equation behaves differently. A chemical rocket has to carry its propellant, which means the launch system has to lift that propellant against gravity, which means most of the launch mass is fuel for the early phase that exists only to move the fuel for the later phase. Even the most efficient chemical and nuclear engines hit a wall well below the speeds people imagine when they say interstellar. The wall is built from the math of carrying your own energy with you. Take the energy out of the craft and the wall moves. A gram-scale sail with a small payload can, on paper, be accelerated to a substantial fraction of light speed by an array on the ground, because the array does not have to come along. That is the launch architecture every honest fast probe concept now lives inside. Lubin's roadmap is the clearest current statement. Breakthrough Starshot is the most famous public application. The system model paper that followed makes the engineering arithmetic explicit. Gram-scale spacecraft, square-meter sails of advanced materials, a kilometer-scale laser array, and a few minutes of acceleration phase. The total launch energy is still enormous, but it lives in the array. The vehicle that crosses interstellar space is, by the time the laser turns off, very nearly empty. Now look at what that bargain has done to the spacecraft. The craft is small, it has no fuel, it has no engine. It has, at most, a small electronics package, some sensors, a tiny transmitter, and a sail that catches stray photons but is no longer being pushed by anything in particular. From the moment the laser shuts down, the craft is a passive object. It cannot speed up, it cannot slow down, it cannot turn meaningfully. The architecture that bought it interstellar speed bought it those things by taking away the parts of a spacecraft that would normally let it maneuver near a destination. The Heller and Hipker study makes that consequence concrete. Their 0.2c flyby case is the same architecture the Lubin roadmap and the Starshot project page describe. The craft reaches Proxima in about 20 years. Then the same craft with no propellant and no onboard engine sweeps through the destination system in hours. That short window is not a flaw in the calculation. It is the direct consequence of the design choice that made the crossing possible. The fast craft is a fast craft because it does not carry the means to slow down. Anything that would let it slow down would also slow down the trip. The trade is everywhere in the literature. Lubin's roadmap is clear that directed energy gram-scale concepts are the cleanest near-term route to relativistic interstellar flight. He is also clear that this lane is, for the moment, fundamentally a probe-first lane. The crafts that the architecture supports are small, simple, and ballistic after the boost phase. Larger payloads need more laser energy, more sail area, longer boost times, and at some point the architecture stops being a sensible answer and starts being a different problem. The boundary is not artificial. It is the natural shape of an engine that lives on the ground. You can also see the consequence in the conversations that show up around the project. When someone asks whether Breakthrough Starshot is going to give us a probe at Alpha Centauri, the most concise summary that keeps appearing is some version of, "This particular mission is a flyby, so no stopping." The reflex toward the stopping question is not a failure of public imagination. It is the public catching up with the architecture. The craft chosen for the first realistic interstellar mission is exactly the kind of craft that has nothing to break with. So the launch bargain is real, and the trap inside it is not hidden. The craft goes fast by being almost nothing. Every system that would have helped it visit instead of pass was left at home with a laser. The mission planner faces a choice that is honest and uncomfortable. Carry more, and you cannot go fast. Go fast, and you cannot stay. Trying to do both in this architecture means designing a different mission. The propulsion conversation does not even need to mention exotic physics. The design lock comes from how the energy is carried, or rather from how it is not carried. There is also a quieter point about timing. The boost phase lasts minutes. The cruise phase lasts decades. The encounter lasts hours. From the project's point of view, the mission is mostly cruise. There is no opportunity during cruise to add a braking system. The craft is already moving at relativistic speed. There is no engine, no propellant, and no place to attach one if it were available. Any braking has to be in the design before launch, or it has to come from somewhere outside the spacecraft entirely. The laser array also has long lifetime advantages of its own. It sits at home with grid power and maintenance crews. Single laser modules can be replaced while the rest of the array keeps working. The array can keep operating across decades, sending probe after probe to different targets. The thing that goes is small. The thing that endures is big. But the same asymmetry pushes the burden harder onto the launch side when you ask it to do more. A heavier payload requires either a longer boost time, which is bad for the sail's thermal handling, or a larger array, which is bad for the construction budget. If the launch bargain has already committed the craft to a flyby, the only way to recover a rival is to add something to the craft, or something to the trip, or something to the destination. The moment you start trying to add it, the launch bargain pushes back. The craft goes fast by being the kind of vehicle that arrives with very little left to help it stop, and the cost of giving it something to stop with starts showing up before the mission ever leaves the solar system. It is worth being precise about why the directed energy lane has the standing it does in the present literature. The serious near-term interstellar work is not really a contest between many architectures. It is a single architecture being studied more seriously than the others because it is the only one whose numbers begin to close. Lubin's roadmap walks through the field carefully. Pure chemical propulsion does not reach interstellar speeds in any survivable time. Nuclear thermal and nuclear pulse concepts are interesting, but require either a fundamentally new engine class or detonation methods that have political and safety obstacles outside any normal program planning. Antimatter propulsion has the storage problem the previous documentary explored at length. Fusion propulsion has its own ignition and exhaust handling problems and remains in research at terrestrial scale. Each of those concepts is a real research direction. None of them currently produces a credible interstellar mission within near-term horizons. Directed energy does, because the engine stays home. But that same fact is the trap. The architectures that close numerically are the architectures that strip the craft of nearly everything that would matter at the destination. The reason chemical, nuclear, and fusion concepts close less easily is that they ask the craft to carry the engine all the way there. The reason directed energy closes more easily is that it does not. A craft that carries no engine is also a craft that has no engine at the destination. The same architectural choice that opens the door to interstellar travel closes the door to arrival there. The two doors are connected at the level of how the engine is carried, or rather where the engine is left behind. There is no clever rearrangement inside the directed energy lane that recovers both. The choice has been made, and it has been made by the same architectural decision that makes the lane plausible in the first place. Now sketch the same craft on the back of an envelope, but this time with a stopping system attached. Pick whatever stopping system you like. A propellant tank with a chemical or ion engine, a second sail far larger than the first, meant to catch incoming starlight at the destination, a magnetic loop carrying superconducting current to push against the interstellar medium, a bank of capacitors to drive an electric sail. Whatever it is, it has mass, structure, and operational requirements, and every kilogram of it has to be accelerated to relativistic speed at the start of the mission. The craft does not have an engine to do that. The laser at home is what has to do it. So the moment you add stopping power, you are not adding it only to the arrival side of the mission. You are adding it to the launch side. That is the central burden. Carrying a braking system means the launch system has to push that braking system to the same speed as the rest of the craft. The energy required to push a kilogram of payload to 0, 2c, is the same whether the kilogram is sail, electronics, or stopping hardware. The laser array does not care. The cost is paid in laser fluence and acceleration time, both of which are already enormous in the basic flyby design and grow with every gram. The result is that even a small braking system on a gram-scale probe pushes the mission out of its design point. Heller and Hipke spell out the consequence in one of the cleanest tables in the interstellar literature. Their work on bound orbit photon sails finds that, for a sail concept capable of decelerating into a captured orbit at Alpha Centauri using only the destination star's light, the feasible injection speed is no longer 0, 2c. It is roughly 1/20th of that, around 0.046c. The trip stops being a 20-year crossing. It becomes something on the order of 95 years to Alpha Centauri A and B, with another 46 years tacked on to reach Proxima. The same family of ideas, asked to do speed and stopping, produces a mission that takes about 7 times longer than the famous flyby case. That is the headline trade in physical language. The mission can be fast, or it can be stoppable. It cannot easily be both with the same hardware. The sail that races to Proxima in 20 years is the sail that cannot stop. The sail that can stop is a different sail, traveling a different speed on a different mission timeline. The bound orbit concept is not a small adjustment to the flyby concept, it is a different mission. You can also feel this in the magnetic sail literature. Claudius Groh works out a scaling law for magnetic braking against the interstellar medium. The result, for a multi-ton mission decelerating from high speed at Proxima, is a spacecraft mass in the range of 1,000 tons. That is not a back-of-envelope mass. That is a mass that brings its own civil engineering vocabulary. A Starshot-style probe is gram-scale because the architecture cannot afford for it to be anything else. A Groh-class magnetic sail braking system is a 1,000-ton vehicle because that is what magnetic braking against a thin medium asks of you when you also want to start from a substantial speed. The two pictures are not on the same shelf. Parakis and Hine, working through combined magnetic and electric sail architectures, show the same pattern from a slightly different angle. Their study finds that a hybrid sail can decelerate a multi-ton spacecraft from about 5% of light speed in roughly 29 years. That is genuinely impressive engineering. It also says, quietly, that the most plausible architecture for stopping at all requires 3 decades just for the braking phase, on top of however long the cruise took. The mission that arrives quietly at the destination spent about 1/3 of its lifetime slowing down. The dream of a Starshot-style flash and the reality of a Parakis-Hine arrival are different mission tempos. The reason the math comes out this way is not mysterious. Slowing a fast object down is, at the level of physics, just as expensive as speeding it up. A mission that needs to remove a given amount of kinetic energy needs to dump it somewhere. If the dumping happens through a rocket exhaust, you carry propellant. If it happens through a sail catching starlight, you carry sail area, and you need that light to be there in the right strength for long enough. If it happens through a magnetic loop interacting with the interstellar medium, you carry the loop, and you need to spend time in the medium. None of those choices are free. Each one is the launch system paying part of the stopping budget in advance, in launch energy or in mission lifetime, and most of them pay it in both. So the simplest possible accounting comes out like this. A mission that crosses interstellar space and stops has, in its design, 3 time budgets, not 1. There is the launch energy spent shoving everything up to cruise speed. There is the cruise spent waiting between the stars, and there is the braking phase, which is often as long as the cruise. That last budget is the part the popular image of interstellar flight tends to leave out, and it is exactly the part the literature keeps lengthening as the concept becomes more honest. Carrying stopping hardware also tightens the failure tree. Every additional system has to survive the cruise. The sail that has to break at the destination has to remain folded or stowed without degradation for decades. The superconducting loop, if there is one, has to hold its current or be re-energized at arrival without the help of any local infrastructure. The braking propellant, if there is any, has to be stored in a stable state for a span longer than any human-built propellant tank has ever been demonstrated to hold. None of these are showstoppers. All of them are reasons that adding a stopping system to a fast probe is not a matter of welding on an extra unit. It is a redesign. There is also a small but important point about the laser array itself. The directed energy roadmap describes an array of phased lasers spread across a kilometer or more of ground, each contributing a small fraction of the total power, with all of them synchronized in phase. The total energy delivered to the sail during the boost phase is enormous. The peak power is staggering. The duration of the boost is short, but the boost is also where every gram of payload pays its laser energy bill. Asking the array to deliver enough additional fluence to push a heavier craft up to cruise speed is not free. The laser cost grows linearly with the payload, and the laser cost was already the dominant capital cost of the architecture. Doubling the payload roughly doubles the launch system. Quadrupling it roughly quadruples it. There is no economy of scale that makes the laser array cheaper per gram as the payload grows. The same physics that lets the array push a gram-scale probe to relativistic speed is what makes pushing a ton-scale probe to the same speed roughly 1,000,000 times more expensive in laser energy. Even a moderate added stopping system, on the order of tens or hundreds of grams of braking hardware, is a substantial multiplicative cost on the launch side. You can also see the burden in the literature's own restraint. The bound orbit photon sail concept, the magnetic sail concept, the electric sail concept, the photogravitational concept, the photogravimagnetic concept, all of them are framed by their authors as specific exercises in burden distribution, not as universal arrival solutions. None of them claim to be the root. Each one carefully identifies the boundary inside which it can do useful work. The pattern is consistent. There is no method in the present literature whose authors say, in their own words, that they have solved interstellar arrival. They say, instead, that they have reduced one part of the problem, while honestly accounting for the parts of the problem they have not solved. That is the field being careful. It is also the field telling the reader that no single bargain has yet shown up that closes the whole arrival case. That is what carrying the burden looks like in plain terms. The ship may fail to stop, because it had to pay for stopping long before it ever saw the destination. The launch bought speed by going light. Stopping asks the same launch to carry weight. The two requests fight each other before the laser even fires. So the next move is not to look for stopping systems hidden in the destination. It is to look at the cleanest braking family in the literature and watch how its mission tempo changes when you ask it to stop. Start with the photon sail, because it is the family the fast mission story already lives inside. A photon sail is a thin reflective surface that gets pushed by light. At the launch end, the light comes from a directed energy array. At the destination, if the mission is brave enough to try arrival, the light comes from the target star. That second use is the one to focus on. It is the closest thing the literature offers to a free braking system. There is no propellant, there is no exhaust, there is only the same kind of sail being used in a different direction, with the destination star doing the work the laser used to do. Heller and Hipke's bound orbit paper is the cleanest analysis of what that looks like for Alpha Centauri. Their concept aims to put a high-velocity photon sail into a captured orbit using only the radiation pressure of the target stars. The arithmetic is honest. They model a graphene-class sail of well-defined area and mass, and they ask what cruise speed it can have if it must arrive slowly enough for the destination starlight to bring it to a bound state before the encounter geometry slips away. The answer is the 4.6% of light speed figure that appeared earlier as the braking burden case. The mission becomes a roughly 95-year crossing for Alpha Centauri A and B. The same sail at 0, 2C can race there, but it cannot stop there. The architecture is essentially the same on launch. A directed energy array still pushes the sail outbound. A graphene-class sail still does the catching. The difference is on the other end. To arrive in any bound sense, the sail has to enter the system slow enough that the destination star's light can slow it the rest of the way. That is a much smaller speed window than the flyby case. There is no way to enter the system at 0, 2C, and use the destination starlight to brake, because the photon pressure of even a relatively bright star, exerted on even a relatively large sail, is small compared with the kinetic energy of a multi-ton, or even gram-scale object moving at 1/5 the speed of light. The sail can either move slowly and let the star catch it, or move fast and let the star slip past it. it cannot do both inside the geometry the actual mission has to live with. Heller, Hipke, and Pierre Kervella sharpened the picture in a follow-up study using photogravitational assists. The idea is more clever, not less honest. Instead of using only photon pressure to brake, the spacecraft uses photon pressure together with gravitational deflection during a close pass to one of the Alpha Centauri stars, with a second pass at another star in the system to bend the orbit into a stable form. With the right geometry, the bound orbit version of the mission can be flown faster than the pure photon braking case. Their nominal graphene-class sail can reach Alpha Centauri in something like 75 years instead of 95, and end up in a stable orbit, with a chance of continuing on to Proxima after another long phase. Hold those numbers next to the flyby. 20 years to a high-speed pass. 75 years to a controlled arrival, with photogravitational assistance in the most optimistic case. The same family of ideas, written into different mission geometries, produces missions that differ by more than a generation. A team that picks the flyby may see results during the working career of the people who built the laser array. A team that picks the bound orbit arrival is launching a craft that will be analyzed by the children of the people who built it, and the results from any extended phase will reach grandchildren. It is worth being careful here about how much of this is a fact about sails in general, and how much is a fact about this specific architecture. The bound orbit and photogravitational concepts are designed around a particular kind of ultra-light sail, with a particular set of material assumptions around a particular pair of stars. They are not a universal arrival recipe. A heavier sail breaks more slowly. A different star pair gives different photon pressures and different geometric options. A different payload mass changes the whole arithmetic. Anyone who wants to extend these numbers to a different mission needs to redo the work, not copy the answer. The literature is consistent about that. But the central lesson does not depend on the details. Inside the photon sail family, every paper that asks the spacecraft to stop adds time. There is no clever variant in which the same sail, with the same launch energy, both flies fast and brakes hard. The bound orbit case slashes injection speed by a factor of 4 or 5. The photogravitational case recovers some of that loss by being smarter about the geometry, but it does not approach the flyby tempo. The trade is built into the physics of how a sail interacts with light. There is no escape inside the family. That is also why the optimism in the photogravitational paper is honest. The authors are not promising a Starshot-paced controlled arrival. They are showing that, within the bound orbit lane, the trip time can be improved with clever choices, and that under specific conditions a sail can plausibly become a long-term resident of the destination system. That is a real advance over earlier work. It is also still a many-decade mission. The improved best case is faster than the older best case. It is far slower than the famous fast flyby. The interpretation boundary matters here. Photogravitational assist is not a general braking solution. It is a clever exploitation of a specific configuration around a specific binary system for a specific sail material. The same trick does not generalize to all destinations or all sails. It is a sign of how flexible the literature can be when it is given a particular case, not a sign that the broader problem has been solved. There is one more useful number to anchor the trade: a photon sail braking architecture that hopes to bind into orbit at the destination is operating in a regime where the photon pressure from the destination star is at most a few hundred watts per square meter at the relevant ranges. Spread across many square meters of ultralight sail, that pressure is enough to apply a small but real force to a few gram payload over the right time interval. The interval in the bound orbit and photogravitational cases is months. The deceleration is gentle. The total impulse summed across the encounter is what brings the sail into a bound state. Multiply the payload by 100 and the photon pressure does not change. The inertia does. The braking time has to grow correspondingly. Multiply the payload by 10,000 and the bound orbit concept stops working in any plausible time frame. The sail family that works at gram scale stops working at meaningful payload scale within its own physics. There is no clever rearrangement inside the family that recovers a multi-kilogram bound orbit at near flyby tempos around Alpha Centauri. That is also why the literature uses ultralight sails as standard cases. Graphene-class materials with mass per area in the milligram per square meter range are not chosen because the authors love novelty. They are chosen because the sail-to-mission ratio that makes bound orbit braking feasible requires the sail material to be extraordinarily light. Heavier sails of more familiar materials like aluminized plastic foils or thin metallic films do not close the bound orbit budget at meaningful destinations. The mission depends on sail materials that are themselves not yet a mature engineering product. Graphene is being developed in laboratories. Sheets of it at the scale a Starshot-class sail requires are not currently a manufactured item. The sail family is plausible because graphene-like materials exist on the lab bench. It is fragile because they have not yet existed at flight scale. So the photon sail family ends up making the title easier to defend rather than harder. The same idea that gets a tiny probe to Alpha Centauri in 20 years cannot, within its own physics, also stop there at a competitive tempo. The arrival mission belongs to a different timeline. The more the sail behaves like a visitor, the less it behaves like the famous fast flyby. That is the first clean case of a braking method that is physically serious, evidence-anchored, and quietly devastating to the popular image of how interstellar arrival might look. Now turn to the propellantless braking concepts that promise to avoid sails entirely. A magnetic sail, in the simplest description, is a large loop of current that carries a strong magnetic field with it as it moves through the interstellar medium. The medium itself is mostly thin ionized gas. As the loop sweeps through that gas, the gas interacts with the magnetic field, and the result is a small but real drag force pointing backward along the direction of travel. There is no propellant on board. There is no exhaust. The drag comes from the encounter with the medium itself. Over enough time, the drag adds up to a substantial change in speed. The craft brakes. The electric sail is the cousin. Instead of a magnetic loop, the electric sail is a set of long charged tethers extending out from the spacecraft. The positive charge on the tethers repels the positive ions in the solar or stellar wind, and that interaction also produces drag. Both concepts are propellantless. Both ask the spacecraft to carry structure rather than fuel. Both depend on the local medium being there in the way the design assumes. Parakis and Hine looked at the two combined. A craft that carries both a magnetic loop and an electric tether can use whichever sail works better at whatever speed it currently happens to have. Magnetic braking is more effective at higher speeds, where the swept gas hits the field with more kinetic energy per particle and drag is stronger. Electric braking helps more at lower speeds, where the magnetic effect weakens and the tether geometry can still grab on to the slow stellar wind. Combined, the two can decelerate a multi-ton spacecraft from a starting speed of around 5% of the speed of light over a span of about 29 years. That number is the same one that lived inside the carried burden argument earlier. Here, it has a different meaning. The arithmetic now is not how to add a stopping system to a fast probe. It is how to design a stopping system that does its own work without needing propellant. The mission tempo is real, the mass budget is real, the braking phase is roughly 3 decades. The vehicle is multi-ton, with sail and tether structure scaling with the load. The architecture is not a gram-scale Starshot-like flash. It is a serious propulsion subsystem with serious mass. Grove's universal scaling relation for magnetic sails shows the other edge of the same idea. He works out how mass and speed scale with each other for a magnetic sail braking mission to Proxima. The bottom of the scaling, where mission speeds are modest and the spacecraft is willing to take a long time, is much friendlier than the top. The top, where speeds approach the Starshot regime and the spacecraft tries to break from there, demands spacecraft masses on the order of 1,000 tons. That is not the kind of number that fits a single launch. It is the kind of number that asks for in-space assembly, dedicated infrastructure, and a different vocabulary about what a starship is. So the propellantless options are not free. They trade propellant for structure, propellant mass for sail mass, propellant tankage for tether length, and a short burn for a decades-long braking phase. The trade can be excellent for certain missions and brutal for others. A modest speed magnetic sail, meant to break from a few % of the speed of light over 30 or 40 years, is a serious concept. A high-speed magnetic sail meant to break from 0 to c, with anything resembling a Starshot-style timeline, is, on present scaling, almost a mission civilization rather than a mission. There is also the destination problem hiding inside the same scaling. The magnetic sail braking model assumes a certain density of interstellar gas, a certain magnetic field structure near the destination, and a certain approach geometry. The electric sail assumes a stellar wind of reasonable density and a particular angle of incidence. None of these assumptions are wrong on average. All of them have substantial uncertainty when applied to a specific destination star that has been studied for a long time but not visited. Forgan, Heller, and Hipke's work on photographomagnetic assists pushes that point further. They look at sails with electrical charge crossing the magnetic structure near Alpha Centauri. The result is interesting and complicated. Charge on a light sail moving through a magnetic field experiences a Lorentz force, and that force can either help brake the sail or kick it off course. Some configurations end up gently captured. Other configurations end up with their trajectory turned in the wrong direction by the same force that was meant to help. The destination is not a passive target. It is a source of fields that can either save the mission or wreck it, depending on how the sail enters, what charge it carries, and what the local geometry happens to be. It is also worth being honest about what is and is not known. The interstellar medium is not uniform. The local interstellar cloud has a known density and known temperature, but the density along a particular line of sight can vary, and the way that medium couples to a relativistic magnetic sail brake depends on details that are uncomfortable to pin down to a few percent. The Garafo, Drake and Cohen study of the space weather around Proxima Centauri b shows the destination side of the same problem. Stellar wind pressure at the planet can be more than 2,000 times the solar wind pressure at Earth, and it varies on day-to-day timescales. A brake that relies on that wind is not relying on a steady backdrop. It is relying on a violent and changing environment. The propellantless concepts are physically serious. They are also reminders that the cost of avoiding propellant is paid somewhere else, in structure, in time, in destination dependence, in mass sensitivity, in charging behavior. The craft might stop without tanks, but only by becoming a larger, slower, more fragile arrival machine, with parts of the braking budget owed to an environment the mission did not get to inspect ahead of time. The propellant problem did not disappear. It was traded for a different problem, which is not the same as a smaller problem. There is also the question of what happens when the loop or the tether fails partway through the braking phase. A propellantless brake does not have an off switch in the same way a thruster does. The magnetic field is created by current flowing in a superconducting loop. If the superconducting state breaks down, perhaps because of a thermal disturbance from a stray cosmic ray or a small mechanical defect that grew over decades, the loop loses its current rapidly. The magnetic field collapses, the drag disappears. The spacecraft continues with whatever velocity it had at that moment. There is no graceful failure mode. The brake is on or the brake is gone. The same kind of risk attaches to the electric sail's charged tethers, which depend on continued high-voltage operation and on the tether structure remaining intact across the cruise. A single torn tether is not a small problem. It is a redistribution of charge across an unbalanced structure, which produces unintended forces and torques. Mission planners have spent decades learning to design around such failure modes for ordinary spacecraft, and the result is usually redundancy. Two of everything. Backup systems for backup systems. That works for an Earth orbit or even a Mars-class mission because the mass cost of redundancy is tolerable. For an interstellar braking subsystem operating across decades of cruise, that redundancy comes with serious mass penalties. The brake that has to work after a long cruise has to be the kind of brake that does not depend on any single component remaining functional. That kind of brake, in current concepts, has not been demonstrated. It is a research goal, not a delivered design. So the field-based stopping families look much less like a silver answer once their assumptions are written down. They look like one more way of distributing the same fundamental cost. Some of that cost lands on the launch system, some lands on the cruise duration, some lands on the destination, some lands on accepted risk that the brake itself will work after 20 years of patient travel. The pattern is the same wherever you push on it. The mission gets to choose how to pay for stopping. It does not get to choose not to pay. When part of the braking comes from the destination becomes part of the spacecraft. That is the small sentence that hides under every propellantless architecture we have just seen. A photogravitational assist depends on the destination star's positions, masses, and luminosities. A photogravomagnetic assist depends on the magnetic field near the destination and the way that field is structured at the moment of arrival. A bound orbit sail depends on the radiation pressure profile around the destination star and the orbital geometry of the system. In each case, the destination is no longer just where the mission is going, it is part of the mission's machinery. That changes how we have to think about places like Alpha Centauri and Proxima. In a generic trip to the stars story, the destination is a postcard. There is a star, maybe a planet, maybe a moon. The narrative arrives and looks around. In the arrival physics version of the story, the destination is active. It has wind, it has magnetic structure, it has a particular brightness profile in the part of the orbit the spacecraft happens to enter. All of those features have to behave in a way the mission designer expected decades in advance, with only the data we currently have from afar. The Garofo paper on the space weather of Proxima Centauri b is one of the clearest examples of how active the destination can be. Proxima is a red dwarf. Its stellar wind, in their model, can exert pressures more than 2,000 times the solar wind pressure at Earth on the planet in the habitable zone. The pressure varies substantially on the day-to-day timescale of the star's rotation and on the longer timescale of activity cycles. That is not a steady backdrop a magnetic sail brake can lean on like a wall. It is a fluctuating environment with strong gusts. A braking system that relies on the wind has to be ready for both quiet days and active ones. And the difference between the two can be large. A photogravitational assist around Alpha Centauri A and B is a different kind of problem. It depends on the precise geometry of approach, the orbital phase of the binary at the time of arrival, and the radiation pressure profile of each star at the relevant wavelengths. The Heller, Hipke and Curvella study spells out concrete trajectories that can put a sail into a bound orbit in the system. Those trajectories work for specific arrival geometries. Different geometries do not work. The mission designer has to choose, decades before launch, a trajectory that will line up with where the stars actually are when the craft arrives. That is a level of choreography that gets less impressive the more you stare at it. Stars also move. Alpha Centauri A and B orbit each other with a period of about 80 years. Proxima orbits the pair on a much longer scale. The system that the mission planner sketches today is not the system the craft will see when it arrives. The geometric configuration shifts in ways that have to be predicted to within reasonable accuracy. That prediction is not impossible. The orbital elements of the Alpha Centauri system are well measured, but the requirement is that we trust those predictions, propagated forward, to the level needed by a mission whose arrival can be wrecked by being a few degrees off. The Forgan paper makes the same point about magnetic structure. A photogravomagnetic assist depends on the magnetic field around the destination star behaving in a particular way during the encounter. The team has to assume that field structure when designing the trajectory. If the local field is different at arrival, either because the star's activity cycle has shifted or because the mission planner's model was incomplete, the assist that was supposed to break the sail can instead deflect it. The literature is honest about this. The same effect that lets the destination star help can also let the destination star hurt. You can also feel the dependence in the way the missions degrade. A flyby that misses the closest approach by a small angle still arrives at the system and still takes pictures. The mission was not particularly choreographed. It was always going to be a tear-through. An arrival-grade mission, in contrast, has a small region of allowed approach angles, a small window of allowed speeds, and a narrow range of allowed local field behaviors. Outside of that envelope, the brakes fail. The sail does not capture. The orbit does not bind. The mission becomes either a strange flyby or a confused escape, depending on which way the geometry went wrong. And this is a different kind of failure mode than the propulsion communities are used to. A normal mission failure is a hardware problem on the spacecraft. The arrival-grade interstellar mission failure can be a hardware problem on the spacecraft, or it can be a behavior problem at the destination star. The mission planner does not control the destination star. They model it. They predict it. They write the trajectory around their best estimate of its behavior, and then they wait for decades to find out whether the estimate was good enough. There is also a quieter point about how stellar systems differ. Alpha Centauri A is a close cousin of the Sun, a G-type star. Alpha Centauri b is a K-type star, cooler and dimmer. Proxima is a red dwarf, smaller and more active. Each of them has a different radiation profile, a different wind, a different magnetic temperament. A braking architecture optimized for one is not automatically optimized for the others. A photon sail that catches enough light from Alpha Centauri A to enter a bound orbit there might not catch enough from Proxima to do the same. A magnetic sail that breaks well in the strong but variable Proxima wind might not be well matched to the quieter winds farther from the red dwarf. The system is not one destination, it is three, each with its own physics. There is also a planning paradox hidden in the destination dependence. The way mission designers usually deal with environmental uncertainty is to gather more data before launch. A Mars mission profile changes as new Mars observations come in. A lunar lander concept refines its landing site choice as new images become available. The lead time for an interstellar mission, however, is so long that the destination data the team has at launch is the data they will have to live with through the entire cruise. The Alpha Centauri system can be observed remotely with current telescopes, and the European Southern Observatory and other facilities have built up substantial knowledge of the orbital geometry and stellar properties. But fine details of the magnetic structure at the moment of encounter cannot be predicted decades in advance. Whatever model the launch team has, it is the model they will have to commit to. Course corrections during cruise are limited or absent. The destination data is a fixed input to the mission's design, and the destination itself is free to change between launch and encounter in ways that the model could not predict. That gives the destination dependence a sharper feel. It is not only that the destination has to cooperate, it is that the destination has to cooperate in a way the mission could already see when it left. The team's model of Alpha Centauri at the time of launch must include a forecast of how the stars will be positioned at encounter, what the wind will be doing in that part of the activity cycle, and how the magnetic field will be structured during the brief window the spacecraft has to traverse it. Each prediction is honest, and each has uncertainty. The cumulative uncertainty has to fit inside the operating envelope of the brake. If it does not, the mission has to either widen the envelope, which usually costs mass, or accept a lower probability of bound orbit arrival. Neither is a small concession. So the destination star, when it is part of the brake, becomes a mission component the team did not build and cannot fully predict. The choreography that gets a sail into a bound orbit at Alpha Centauri only works for a specific approach and a specific configuration of the destination system. The wind that breaks a magnetic sail at Proxima only breaks that sail for a particular distribution of wind speeds and densities. If the destination does not cooperate in exactly the right way, the ship still does not arrive under control. Cooperation is not optional, it is part of the design, and the destination, decades before encounter, signs no contracts. Return to that small craft entering Alpha Centauri at 0, 2C. Imagine the instruments are working. The camera, the magnetometer, the dust counter, the small spectrometer, all powered up. The transmitter is ready. The flight computer is running through its observation schedule, and the timer beside the trajectory plot says the entire pass through the inner system will take a few hours. Inside those few hours, every science measurement the mission will ever make has to happen. Every image, every field reading, every spectrum. There is no second pass, there is no orbit, there is no later. That is the science geometry of the flyby. It is not failed science, it is compressed science. It is what a fast probe with no braking system can offer. The Heller and Hipke paper notes the pass duration as a few hours for the 0, 2C case. The Breakthrough Starshot project page describes data collection during transit. The mission concept is consistent. The flyby will produce science. It will produce it inside a window the mission cannot extend. You can feel the difference by setting the flyby beside a more familiar planetary visit. The Cassini mission at Saturn ran for over a decade. It made repeated passes by the same moons, in different lighting, at different angles, with different instruments active. When something interesting appeared in one pass, the team could plan the next pass to look more carefully. New Horizons at Pluto ran its main science in roughly a day, but the team had spent years thinking about which questions to prioritize during that single encounter. They knew in advance which targets to point the camera at, in what order, with what exposure. They got the answers because the engineering, the planning, and the geometry all aligned for that one careful day. An interstellar 0, 2C flyby is the same kind of one-shot, but with much less control. The encounter geometry is determined by the laser boost a generation earlier. The cameras have to fire on a predetermined schedule. The transmitter has to be ready to start sending data the moment the pass begins. The science team back home does not get to look at the first image and then ask the spacecraft for a second one. Even if they could, the time delay would be over 4 years one way. The mission lives or dies on the planning that happened before launch. So the kinds of questions a flyby can answer are different from the kinds an orbiter can answer. A flyby can take pictures of a planet from one angle at one moment in one phase of its rotation. An orbiter can take pictures of a planet from many angles at many moments in many phases and stitch the results into a global map. A flyby can sample the magnetic field along one short trajectory through the system. An orbiter can sample it for months, mapping how the field varies with time and position. A flyby is a measurement. An orbiter is an instrument that can keep returning to the question. There is also a real consequence in how the data gets home. Kevin Parkin's analysis of a Starshot communication downlink is detailed and sober. The transmitter on the gram-scale probe is small. The link budget is governed by the receiver size at the solar system end, the antenna gain on the probe, the integration time, and the geometric configuration. During the close approach to the destination star, the probe is near a bright source. The geometric alignment is dictated by the trajectory, and the transmitter is competing with stellar radio noise as the angles change. After the encounter, as the probe pulls away from the star, the alignment improves and the link budget gets better. The mission is most photogenic at the moment when its communications are worst. That is a strange constraint to design around. The instrument is taking its most valuable data exactly when sending the data home is hardest. The mission's response, in the published concept, is to store the data on board and transmit it after the encounter as the geometry improves. The trajectory still goes out the far side of the system, and the spacecraft can spend years downlinking what it captured during its brief visit. That works mathematically. It means the team on Earth gets the answer to "What did we see?" only after the spacecraft is already long past the destination, moving steadily into interstellar space on the other side. Even with that workaround, the science return is different in kind from an orbital mission. The team gets images and measurements from one moment, with no opportunity to follow up. If a strange feature appears on a planetary surface in one image, there is no second image at a different angle to confirm it. If an unexpected magnetic anomaly shows up in the field data, there is no way to send the probe back to map it. The mission produces a snapshot of another star system, taken once at a specific instant, with whatever instruments survived the cruise and worked in the encounter window. The picture can be magnificent. It is, by construction, only one picture. There is also the question of what a flyby does to the cultural meaning of arrival. Voyager passed Saturn in 1980. The images were beautiful, the science was important. We do not, in common speech, say Voyager arrived at Saturn. We say it visited. We say it passed by. The word arrival is reserved for missions that stayed: Galileo at Jupiter, Cassini at Saturn, Juno at Jupiter. Whether or not those distinctions are explicit, they are how the field naturally talks. A first interstellar flyby will be a major historical event. It will be a brief one, and it will sit in the catalogue of human spaceflight beside the planetary flybys, not beside the orbiters. It also matters that the science compresses unevenly. Some things, like the bulk composition of the destination system or the gross magnetic structure on the encounter side, can be measured in a fast pass. Other things, like the detailed magnetic field structure across a full orbit, the climate of a planet over time, the variability of a star, or the dust distribution far from the immediate trajectory, cannot. The mission gets what the encounter geometry allows. The rest stays out of reach until the next mission, which has to make the same trip with the same constraints again. There is also a subtle complication for the science team in how the data has to be interpreted. A flyby produces a snapshot, but it produces it from a particular angle, in particular lighting, at a particular moment in the destination's various cycles. The team has no way of asking whether the planet they imaged is normally that bright, or whether the magnetic anomaly they recorded was a regular feature or a temporary fluctuation. Calibration against repeated observations, the way planetary scientists routinely calibrate Voyager and New Horizons data against subsequent missions and Earth-based telescopes, is much harder. The flyby data has to be interpreted on its own. The team will, no doubt, work hard to extract every bit of information from it. They will also know they are seeing the destination once, with no opportunity to revisit and check. That changes the kind of scientific claim a flyby mission can ground. Strong claims about persistent features of the destination system are difficult to defend from a single observation. Strong claims about the geometry of the encounter itself, which the spacecraft can measure directly, are more secure. Strong claims about, for example, the magnetic field structure at one specific point in time along the trajectory are reasonably defensible. Strong claims about what the system as a whole is doing in some average sense are harder. The flyby is best at measuring what was happening at the moment of the pass. That is enormously valuable as a first interstellar measurement. It is also a different kind of evidence than a years-long resident program would produce. So the first flyby pays off the title's promise in a real but limited way. The craft can return historic data. It will not return resident data. The destination becomes a measurement event the mission cannot repeat. Without stopping, the first Starship may arrive only as a measurement event that cannot linger. That is not a moral judgment about the mission. It is a description of what kind of mission has been chosen. The choice is forced. The geometry is the geometry. The flyby gets what it gets and asks the next mission to bring more. While the flyby is being celebrated for what it can do, the spacecraft has already been doing something quieter for 2 decades. It has been crossing interstellar space. The medium between the stars is mostly empty by any normal standard, with around 1/10 of an atom per cubic centimeter in the local interstellar cloud. But at relativistic speed, even a thin medium becomes a steady rain of impacts. The hydrogen and helium atoms are essentially stationary in the galactic frame. The spacecraft is the thing moving. From the spacecraft's perspective, the atoms come straight at it, at near light speed, in a continuous stream. Over 20 years of cruise, that stream is a substantial dose. Home, Lazarian, Burkhardt and Loeb worked out the consequences for a relativistic probe in their 2016 paper on the interaction of fast spacecraft with the interstellar medium. The results are not subtle. Even at modest interstellar gas densities, a craft moving at 0.2 experiences significant erosion of its leading surface. Tiny dust grains, by far the most damaging components of the medium, deposit energy in pits and craters that grow over the cruise. Larger grains, much rarer, can punch through thin foil. The cumulative effect is that the leading face of the sail and the forward edges of any electronics package are slowly worn down across the trip. The cruise is not benign. It is an extended low-intensity impact test the craft has to survive. Kelvin Long's 2023 analysis sharpens the picture for the Starshot case specifically. He estimates that a gram-scale 0.2 probe needs something on the order of 1.4 to 3 millimeters of forward shielding to survive the cruise to Proxima with most of its instruments intact. That shielding costs between roughly 1% and 5% of the total mass, depending on material choices and exact geometry. For a gram-scale probe, 1 to 5% is not a rounding error. It is a real fraction of the mass budget, sliced off the science and structural allocations to keep the rest of the craft alive. The shield itself is, in a sense, sacrificial. It absorbs the impacts so the craft does not have to. That has consequences for the kinds of arrival just sketched. A sail that is being worn down by interstellar dust for 20 years is not the same sail that left the solar system. Its reflectivity has changed. Its surface flatness has changed. The thin foil at the front of the craft has thinned and pitted unevenly. When the destination star's light tries to push on that sail for braking, the sail no longer has the optical properties the original design assumed. The brake is real. The brake is also degraded. The probe's instruments face their own version of the same problem. Cosmic rays during cruise, plus the steady dust impacts, plus thermal cycling as the craft moves away from the Sun and then toward Alpha Centauri, all contribute to slow degradation of the electronics. A flight computer that worked perfectly at launch may be running 2 decades later, with a higher single-event upset rate, more memory errors, and slightly degraded sensors. The probe arrives at the destination with less of itself intact than it had at launch. That is true even for a probe that takes no exotic damage at all. It is the baseline cost of crossing a 4 light-year corridor at relativistic speed. The Lubin roadmap puts the same problem in slightly different language. a gram-scale interstellar probe is by design fragile. Every gram of mass is doing real work. The shield has to be thin enough to allow the mission, thick enough to allow the survival. There is no extra mass for redundancy, no spare instrument, no backup sail. The mission is not a Voyager-class vehicle with margin built into every subsystem. It is closer to a single-shot device, optimized for one trip with no error recovery. The trade is honest, the roadmap is clear, that the architecture is plausible because the payload is small, and the payload is small because the architecture cannot afford it to be otherwise. The same logic that makes Starshot a serious concept makes its margins slim. Now braid those two strands together. The arrival concept, in the bound orbit case, depends on a precise sail behaving in a precise way when it encounters the destination star's light. The cruise process, regardless of architecture, slowly degrades that sail. The longer the cruise, the more damaged the sail, the less reliably the brake works. The bound orbit case also wants slower cruise speeds, which gives the dust more time to erode the structure on the way. The architecture that helps the brake hurts the survival, and the architecture that helps the survival hurts the brake. Both ends of the design are pulling against each other in the cruise duration. The destination side gets harder too. A magnetic sail that meant to brake against the stellar wind at Proxima depends on the loop holding its current and the structure holding its shape after 20 or more years of cruise. The same dust that pitted the photon sail also struck the magnetic loop's support structure. The cryogenic system, if any, has been running for decades by the time it is needed. The electronics that drive the loop have been exposed to interstellar radiation for the full cruise. The brake is intended to fire after a quarter century of degradation. The mission planner has to budget not only for the structure that arrives, but for the structure that arrives after 1,000 small wounds. There are honest limits to how worried one should be about all of this. The Hong papers do not claim that any specific Starshot-style probe is doomed. They quantify the hazard. The long analysis gives a working shield budget. The Lubin roadmap gives a working architecture inside which the trade is tight but not absurd. Real progress in material science could lower the cost. Real progress in propulsion could shorten the cruise, which would lower the integrated damage. The first interstellar craft is not necessarily condemned to fail. It is, however, condemned to make every part of its arrival depend on hardware that has been quietly worn down for 20 years before the destination begins. It also matters that the dust environment is not perfectly known. The local interstellar cloud has been measured along sightlines toward bright stars with absorption line spectroscopy and ultraviolet observations. The density between us and Alpha Centauri is reasonably well constrained on average. The fine-scale structure, however, is not. There may be small, denser pockets along the line of flight. There may be regions that are more depleted in larger grains, and others that are less so. The mission cannot survey its own path in advance with any confidence at the scale of a few meter-wide craft moving at 0, 2c. The cruise damage is therefore a planning problem with built-in uncertainty. The Hong and Long results give the average expected damage. The actual mission gets the path it gets, and the path may be quieter or noisier than the average. The mission planner has to design for a band of outcomes rather than a single one. There is also a subtler consequence for any architecture that combines fast cruise with destination braking. The optical surfaces and the magnetic structures the brake depends on are exactly the ones the dust would have most reason to damage. The leading face of the sail is what gets pitted. The forward edges of the magnetic loop, if there is one, are what get worn. The brake is not protected from the cruise. It is on the front of the spacecraft, exposed to the medium throughout the cruise, and asked to perform at the end of all that exposure. Designing the brake to be robust against decades of small impacts is a real engineering ask. It is not unlike the kind of demand a planetary entry system has to meet, except that the planetary entry system survives only a few minutes of severe heating, while the interstellar brake has to survive 20 years of slow erosion before its few minutes of needed performance. So the ship may fail to stop not only because braking is hard, but because the crossing already spent part of the mission budget. The fast probe is, in a real sense, two missions, the one that crosses and the one that does whatever the original design intended at the other end. The first mission cuts into the second one's margin throughout, in small, steady ways, that the planner has to fold into every design assumption. By the time the destination arrives, the craft has already paid a tax that the launch budget did not list explicitly. That payment shows up at the destination as a slightly worse sail, slightly noisier electronics, and a slightly less capable mission. The architecture has to absorb it. The brake has to work anyway. There is a different way for a fast probe to fail the destination, and it does not require a single dust grain. It only requires the craft to fly fast enough through enough thin gas. Huang and Loeb laid out the picture in 2017. A spacecraft cruising at relativistic speeds collides with neutral hydrogen and helium, and those collisions can knock electrons free or capture electrons depending on geometry and energy. The cumulative effect is that the craft slowly acquires charge. It is also bathed in ultraviolet starlight, which can drive photoemission of electrons from the surface, adding to or subtracting from the charge depending on the materials. The net result is that the spacecraft does not stay electrically neutral. It carries a slowly evolving electric charge across the full cruise. A charge on a moving body in a magnetic field experiences a Lorentz force. The interstellar magnetic field is weak by laboratory standards, in the range of microgas along most paths. But weak does not mean zero. Over a cruise of years, even a small force applied steadily produces a measurable acceleration in the direction perpendicular to the velocity in the field. The trajectory of a charged relativistic probe bends slightly as a result. The bend is not in the original design. It is something the craft picks up along the way, set by the medium it happens to traverse. There is also a torque story sitting next to the deflection story. A charged spacecraft of irregular shape can experience torques from the same interaction with a magnetic field. Huang and Loeb show that those torques can drive the craft into oscillation, where the sail or the body of the craft begins rotating around an axis at a rate set by the geometry of the charge distribution and the field strength. The rotation is slow on human timescales. Over a 20-year cruise, it can become significant, especially for a sail-class craft whose shape and pointing matter to the science. A sail that arrives at the destination spinning is not the sail the bound orbit mission needed to find there. So now stack those effects on a Starshot scale 0 2C probe. The probe is gram scale, with a sail of square meters spread thin behind it for the boost phase. After boost, the sail may be either retained or jettisoned depending on the design. Either way, the structure is non-spherical, non-uniform, and electrically not balanced. The cruise lasts 20 years. The interstellar magnetic field is weak but ever present. The cumulative deflection and the cumulative torque both have time to act. The probe that was aimed at a particular point in the Alpha Centauri system at launch is not the probe that arrives at that point. The Forgan, Heller, and Hipke paper on photogravimagnetic assists picks up the same physics at the destination end. A sail carrying charge, crossing the magnetic structure near a destination star, is subject to a Lorentz force that depends on the local field. In some configurations, that force adds to the braking action of the photon pressure and the gravitational deflection. In other configurations, it kicks the sail off the intended trajectory. The same effect that is supposed to help the sail capture into a bound orbit can, on a slightly different approach, send it tumbling out of the system in a direction nobody planned. The destination's field is not always cooperative. It can be neutral, helpful, or actively harmful, depending on the choreography. That makes the navigation problem stranger than it sounds. A normal spacecraft mission targets a point in space and then makes small course corrections along the way. An interstellar probe in the published Starshot concept has very limited course correction ability. There is no propellant, there is no thruster. The sail, after the boost phase, is essentially ballistic. Whatever it picks up during cruise, it carries to the destination. If the cumulative Lorentz deflection is significant, the only correction available is at the laser end, where the boost phase aims the craft. There is no in-cruise steering. The aim is set decades in advance and frozen. You can also see the consequence in mission planning timelines. The team that designs the boost phase has to model the cumulative cruise effects on charge, on torque, on deflection. They have to estimate the interstellar magnetic field along the planned line of sight, the gas density along that line, the ultraviolet flux from the Sun and the destination stars, the relative geometry of the destination system at the moment of arrival, and the local magnetic geometry near the destination star at that moment. Each estimate has uncertainty. The cumulative effect of those uncertainties on a craft with no in-flight correction is that the actual encounter geometry is a probability distribution rather than a single point. The mission's job is not to hit a target. The mission's job is to keep that distribution narrow enough that the science still works. That distribution narrowing is not a small problem. A sail aimed at the inner system at Alpha Centauri can, with modest cumulative deflection, end up passing through the system many astronomical units off course. At interstellar distance, even a small angular error translates into an enormous miss. The science instruments, which were already constrained to a few hours during the encounter, get fewer of those hours if the geometry shifts. A close planetary flyby becomes a far-off survey. A bound orbit capture becomes an escape. A photogravitational assist becomes a kick into empty space. The probe still arrives in some sense. It does not arrive where the mission needed it to be. This is also why the literature treats interstellar targeting as a real engineering problem rather than a footnote. A flyby that misses cleanly is still scientifically useful in some configurations, because the spacecraft can return distant imaging and field measurements from a wider angle. A bound orbit attempt that misses cleanly is essentially a failed mission. The sail does not capture. The arrival does not happen. The mission becomes a strange long-distance pass, with the destination receding rather than approaching, and the team back home receiving images of a star system seen from outside it. You can also feel the cost in the architecture choices. A heavier, less charged spacecraft is less susceptible to Lorentz deflection. A more compact, more symmetric craft is less susceptible to torque-driven rotation. A slower cruise gives less time for cumulative deflection to act. Each of those defenses, again, trades against something. Heavier means slower. More compact means smaller payload. Slower means longer mission. The arrival problem reaches back into the launch architecture once more, and asks the design to make trades that the speed-focused concept did not want to make. It also matters that the targeting demand is asymmetric in a particular way. A flyby that is slightly off course in the encounter geometry still produces useful science. The cameras still take pictures, even if those pictures are from a slightly different angle than planned. The magnetometer still records a profile, even if the profile is along a slightly different traverse. The mission degrades gracefully when its aim is off by a small amount. A bound orbit arrival, in contrast, fails catastrophically. The brake either captures the sail or does not. The orbit either binds or does not. A miss of even a small angle means the sail simply continues out of the system. There is no graceful degradation. A mission that is sensitive to charge-induced deflection in this way is much more fragile in arrival mode than in flyby mode. The brake amplifies the consequences of the cruise. There is also a quiet effect from the boost phase itself. The directed energy boost imparts velocity, and along with that velocity it imparts small uncertainties in the direction of motion. Phase errors across the laser array translate into small angular errors in the boost vector. Those errors are folded into the cruise as initial conditions, and each one, multiplied by 4 light-years, ends up as a position error at encounter. The laser team can characterize their array and tighten the tolerances, but they cannot drive the error to 0. The residual aim error, combined with the cumulative Lorentz deflection, defines the probability distribution of where the spacecraft actually arrives. So the probe can quietly miss the very system it was aimed at after 20 years of patient travel, because of a force it picked up during the cruise. The miss is not dramatic. It is a degree or two of trajectory bend integrated over 4 light-years that happens to be in the wrong direction at the wrong moment. A ship that misses cleanly never even gets the chance to discover whether it could have stopped. The braking debate moves to the next mission, which has the same problem to plan around. The first probe that arrives may, with bad luck, be the second one launched, with the first one having drifted off into interstellar quiet without ever crossing the inner system at all. Pull back from the gram-scale sail for a moment and look at the cultural picture the word starship tends to summon. It is large. It has engines on the back. It carries people, or at least substantial cargo. It looks like a thing that could approach a planet, slow down, and orbit. The popular image of a starship is, almost by reflex, the image of an arrival vehicle. It is built around the assumption that the spacecraft is doing more than passing through. Almost nobody pictures a gram-scale sail when they hear the word starship. The literature, in contrast, almost never describes a serious near-term interstellar craft that looks like that popular picture. The credible fast concepts are gram-scale. The credible slower concepts are heavier, but their slowness is part of the trade. The architectures that scale closest to a popular starship image are the ones that ask for tens or hundreds of tons, decades or centuries of crews, in-space assembly, and infrastructure that does not exist yet. The gap between what the word starship makes people imagine and what the evidence supports is wide. Most of the argument so far has been working in that gap. Lubin's roadmap is explicit about the scaling. The directed energy architecture works because the craft is small. A scaling argument runs through the whole paper. The laser energy required for boost is proportional to the spacecraft mass. The fluence on the sail is proportional to the laser energy. The sail area required is proportional to the spacecraft mass. The acceleration phase length is proportional to the spacecraft mass. The whole architecture scales with the gram of payload. Push the payload up to kilograms, and the laser energy required is 1,000 times higher. Push it to tons, and the architecture has to start asking whether it would not be cheaper to build a different engine altogether. The fast lane is fast because it is light. You can see the same scaling on the braking side. Grove's magnetic sail concept gives mass versus mission curves that grow rapidly with payload. A multi-ton magnetic sail braking mission to Proxima at modest speeds is large but tractable. A magnetic sail braking mission for a substantially larger payload at the same speeds is much larger, and at high speeds becomes the kiloton mission referenced before. There is no clean way to grow the payload without growing the spacecraft. The braking systems do not scale gently. They scale steeply. The dust shielding budget shows the same pattern. Long's analysis is for gram-scale probes. The 1.4 to 3 mm of shielding is calibrated to that mass class. Scale the payload up by 1,000 times, and the shielded area grows. The mass of the shield grows with the area. The mission's effective payload, after shielding, grows much less. A larger ship at the same speed is not just a larger ship. It is a larger ship that has to spend a larger fraction of its mass on survival. The scaling does not get better as the mission gets more impressive looking. It gets worse in subtle ways at every step. Then add the destination side. A bound orbit photon sail braking concept depends on the sail being large enough relative to its mass to capture useful photon pressure. A larger payload makes that ratio harder. A magnetic sail braking concept depends on a loop large enough to encounter enough medium to brake. A larger payload makes that loop larger and heavier. A photogravitational assist depends on a sail that responds to the destination star's light. A larger sail catches more light, but it also has more mass to slow down, and it has to be more rigid to keep its optical shape. None of these systems scale to popular image starship sizes without becoming a fundamentally different machine. So the natural conclusion of the propulsion and braking and shielding work is that the first interstellar success is going to look small, not because nobody wants larger ships, and not because larger ships are physically impossible, but because the architectures that get something there first are the ones that minimize mass. Larger ships are a different timeline. They might come later. They might not come at all in any near horizon. The fast probe is the only currently credible bet for the first crossing. You can also see this in how the popular discussion drifts. On forums where people discuss interstellar flight, the moment a project like Starshot is mentioned, the conversation rapidly slides toward what the mission can or cannot do. Quickly someone points out that it is a flyby, not a stop. Quickly someone else asks about scaling it up to carry instruments, or people, or cargo. The answer the more careful posters give is usually a version of the same point. Scaling that architecture is hard in ways the headline does not advertise. The discussion bumps into the same wall the literature describes, often without knowing the references. There is also a reasonable defense to make for the popular image. The word starship is not a technical term. It is a cultural image that has shaped how people picture interstellar travel for a century. Saying that the first realistic interstellar craft is gram scale is not denying anyone's right to dream about larger ships. It is just being honest about which kind of craft has the strongest case to arrive first. The dreams about larger ships do not go away. They simply move to a different timeline with their own set of physics challenges that the gram-scale concepts get to dodge. A different way to put it, the launch problem and the braking problem and the dust problem and the targeting problem are all problems that get worse with mass. The mass scaling is not a coincidence. It is the same physics showing up on different stages. Every kilogram of spacecraft that has to be accelerated, decelerated, shielded, and aimed costs energy, time, and structural margin. The architecture that minimizes mass minimizes all of those costs together. The architecture that does not multiplies them. There is no way to escape that pattern by being clever about one subsystem. The pattern lives across all of them. There is also a quieter constraint from the laser side. A directed energy array sized for gram-scale payloads is already at the limit of what current laser technology and current grid power engineering can deliver. The Lubin roadmap discusses peak powers in the gigawatt range and total energies that compare with the output of a large power station for the duration of a boost phase. Scaling that array up by orders of magnitude is not impossible in principle. It is, however, a project whose cost dwarfs any single space program of the present era. The laser is not the spacecraft, it is the bottleneck. Building a laser that can push a ton-scale payload to zero. 2C is a national-scale infrastructure project comparable to building a particle accelerator larger than any in operation today. A society able to commit to that scale of effort could perhaps build it eventually. A society in our current shape would have to reorganize large parts of its science and energy budgets to fund it. You can also see the scaling problem in the boost phase timing. The Starshot baseline has a boost phase of minutes. During those minutes, the laser delivers enormous energy to the sail, which has to absorb the heat, maintain its shape, and avoid being torn apart. A heavier payload requires either more laser power for the same boost time, which makes the heat handling problem harder, or a longer boost time, which makes the sail's exposure to the beam longer, and which extends the geometry of the laser-sail interaction. Both options run into engineering walls quickly. The sail material is sensitive to temperature. The pointing accuracy is sensitive to the duration. The structural integrity is sensitive to the impulse. Larger payloads do not just scale the laser, they scale every part of the boost phase engineering, and many of those parts are not friendly to scaling. So the popular image of a starship is, for the first interstellar success, the wrong image. The first ship to reach another star may stop being a starship in the ordinary sense long before it tries to stop in the physical sense. It may have already, in the design phase, become something more like a postage stamp scout with a sail sent out by a laser array, expected to take a single set of pictures during an hours-long pass and never expected to return. That is a magnificent mission. It is not the mission the word starship encourages people to imagine. There is still one more piece of the popular image that has to be addressed honestly. Many of the people who care about interstellar travel care because they imagine, somewhere in the back of the story, humans crossing the same distance. Not necessarily in the first mission, but eventually. The word starship is bound up with that hope. So the question worth asking is whether the difficulties that already strain a gram-scale probe become easier, the same, or harder when the mission has to carry people. The answer the evidence supports is the harsh one. They become harder. Start with the crews. A gram-scale probe can lose a few % of its mass to shielding and still work, because everything else on board is tiny and minimum. A crewed ship has to carry people, life support, food, water, radiation protection, habitation volume, attitude control, communication systems, redundant power, and equipment for arrival operations. The vehicle is not gram-scale, it is many tons at minimum. Each ton has to be accelerated to cruise speed. The launch problem is now thousands of times larger than the Starshot case. The directed energy roadmap, optimistic as it is, does not extend cleanly to that regime. Lubin's analysis is clear that a kilometer-scale laser array meant to push grams is not the same machine as one meant to push tons. The architecture for tons is a different architecture, with its own set of unsolved problems. The cruise also becomes more dangerous. The harm, dust and erosion results scale with the surface area exposed to the medium. A larger ship has a larger forward surface and accumulates damage in proportion. The long shielding analysis was for grams. Scale it to a crewed ship, and the shielded forward face is square meters at least. The shielding mass to keep instruments and crew safe is now a substantial subsystem of the spacecraft. Each ton of shielding has to be accelerated. Each ton accelerated demands more energy from the launch. The mass scaling that hurt the gram-scale probe hurts the crewed mission worse. Then the radiation exposure problem. Home and Loeb's calculations on charge and on the interstellar medium also include the dose absorbed by a relativistic craft. The crew's environment, for a craft moving at significant fractions of the speed of light, is not just dust. It is also energetic particles from the medium, blue shifted into harder gamma rays in the craft's frame, plus the cumulative galactic cosmic ray dose. For a probe, this is a hardness problem for electronics. For a crew, it is a survivability problem for bodies. The dose limits for human crews on Mars missions are already a significant fraction of mission planning. The dose for a multi-decade interstellar cruise at relativistic speed is much higher. The shielding mass required is correspondingly larger. The crewed cruise also requires life support that has to function for decades. The longest demonstrated closed-cycle life support systems on Earth have run for months to a year or two, with varying degrees of success. The International Space Station has operated for over 2 decades, but it is regularly resupplied. A truly closed life support system that works for the duration of an interstellar cruise without resupply is not currently engineered hardware. It is a research challenge. The crew has to survive on a system that has to perform across a span longer than any analog program has tested. The risk is not abstract. It is the kind of risk that programs accept only when the alternative is unacceptable. Then arrival. The braking arithmetic that hurt the multi-ton spacecraft hurts the crewed spacecraft more. Parakis and Hein's combined magnetic and electric sail can decelerate multi-ton missions from a few % of light speed over decades. A crewed mission, if it has to start from a higher cruise speed to keep the trip humane in length, has even harder braking demands. If it is willing to take longer, the cruise becomes generation ship territory, with its own set of unresolved problems about whether the crew arriving is even the crew the program designed for. The trade between cruise speed and braking burden, which already hurt the probe, hurts the crewed mission across several axes at once. The destination problem also changes. A probe can take whatever the destination star happens to be doing. A crewed mission needs the destination to be tolerable enough for the crew to survive once they arrive. Garaffo's results on Proxima space weather are not a minor footnote at the destination. They become a habitability constraint for any crew that arrives in the planet's vicinity. 2,000 times the solar wind pressure at Earth is a different magnetic and radiation environment than human spaceflight has ever encountered. The crewed mission has to plan not only for arrival, but for surviving the arrival environment, which is not Mars and is not the Moon. There is also the question of mission duration. A probe that takes 75 years to arrive at Alpha Centauri can be designed to last 75 years. A crewed mission that takes 75 years to arrive is a generation ship problem. The people who arrive are not the same people who left. The mission has to plan for births, deaths, education, social structure, and accumulated equipment failures across multiple human lifetimes. None of that is impossible. All of it is currently outside the experience of any human mission. The risk profile changes from engineering survival to civil society in a metal can, which is a different field with its own deep uncertainties. A reasonable response to all of this is to slow down. A crewed mission could, in principle, fly much more slowly than a 0-2C probe, on the order of a few % of light speed, with correspondingly lighter braking demands. Magnetic sails, or hybrid systems, become more plausible at those speeds. The arrival becomes more controllable. The crossing becomes much longer. A few % of light speed crewed crossing to Alpha Centauri is on the order of a century or more. The mission becomes a multi-generation project. Some people would argue that this is the only realistic crewed interstellar architecture. Others would argue that it is more theater than transportation. The literature does not resolve that debate. It only confirms that the trades involved are even harsher than they were for the probe case. There is also a quieter problem that does not show up in the propulsion versus survival arithmetic, but matters enormously for any actual crewed program. The mission requires confidence that the destination is worth arriving at, a robotic probe can be sent on the basis of curiosity. A crewed mission requires a target that is sufficiently understood that the crew has reason to believe their arrival accomplishes something. The current state of exoplanet science includes a confirmed planet around Proxima Centauri, in the habitable zone by most reasonable definitions, but the planet itself is known only as an indirect signal. Its actual habitability is largely unknown. Its surface conditions are largely unknown. Whether a crewed mission to that planet would find a place suitable for any landing is a question that has not been answered. A robotic mission can find out and report. A crewed mission cannot be sent on the assumption that the destination is friendly. The first crewed interstellar mission, if one is ever planned, will almost certainly follow many decades of robotic reconnaissance that establishes whether the destination is worth the trip. The probe first sequence is not a matter of preference, it is a matter of due diligence. There is also a programmatic point. A multi-generation crewed mission requires institutional continuity across far longer than any contemporary institution has demonstrated. Companies do not last a century. Governments change shape. Even great scientific programs shift their priorities over the lifetimes the mission would require. Some past societies have undertaken multi-generation projects, like medieval cathedral construction. None of those projects require the same combination of technical precision, ongoing scientific input, and continuous funding that an interstellar crewed mission would. The pattern is not encouraging, so the popular picture of a starship as a crewed vehicle quietly recedes when the architecture has to be honest. The mass scaling, the dust, the radiation, the life support, the braking, the destination environment, and the mission duration all get harder with people on board. None of them get easier. If probes barely make the stopping problem manageable, human arrival makes it harder still. The first realistic interstellar mission in any current published architecture is not crewed. The first crewed interstellar mission, if it ever comes, is going to look very different from any of the missions being discussed today, with a different timeline, a different vehicle, and a different set of accepted risks. That mission is not on the near horizon. The closer horizon belongs to the probe. Now collect what the argument has built so far. The launch architecture for the fastest serious interstellar concept is gram scale and flyby shaped. Every braking method either adds mass, adds time, depends on the destination, or all three. The photon sail family can do speed or stopping, but not both at competitive tempos. The magnetic sail family can stop, but only by becoming heavy and patient. The destination depends on cooperation it cannot guarantee. The cruise itself wears down the spacecraft through dust and radiation. The trajectory bends slightly under cruise-acquired charge. Larger ships make every one of these problems worse. Crewed ships make them harder still. Stack the constraints and a strong forecast falls out the bottom. The first successful interstellar mission, under current physics and current architectures, is overwhelmingly likely to be a flyby. Not because flybys are easier in some loose sense, because the architectures that have working math behind them are flyby architectures, and the architectures that could in principle stop are at least a generation slower, heavier, or more expensive in ways that push them later in any realistic program planning. The first ship to cross interstellar space is the ship that does not stop. The first ship that stops is going to be a different ship, built around different bargains, and most likely launched at least a generation later. The Heller and Hipke arithmetic frames the timeline cleanly. A 0. 2C flyby reaches Alpha Centauri in about 20 years. A bound orbit arrival on the same sail concept takes around 95 years. A photogravitationally assisted arrival, in the best case in the literature, takes about 75. Add launch preparation, post-arrival science and downlink, and the practical mission timelines compound. A program that wants results in a working career chooses the flyby. A program that chooses arrival is committing to results that will arrive after most of the people who designed the mission have died. The choice is not subtle. Add the production side reality. A gram-scale probe is small enough to be built and tested with current materials. The laser array is hard, but it is the kind of hard that engineers can quantify and price. A multi-ton magnetic sail braking mission, in contrast, is a vehicle whose subsystems do not yet exist at flight quality. The superconducting loop, The multi-decade cryogenic system, the structure that holds shape through decades of cruise, all of these are research-grade problems. They are not unsolvable in principle. They are not currently scheduled for delivery. A program that wants something to happen this century picks the smaller, faster, less stoppable craft. Add the budget reality. Programs that take a working lifetime to deliver results are programs that survive funding shifts, political changes, and shifts in scientific priority. A 20-year flyby barely fits inside that envelope. A 95-year arrival certainly does not. Real interstellar missions are funded by societies that have to commit to them through generations. The history of large science programs is consistent. Programs that deliver visible results within a working career attract sustained funding. Programs whose first result is 2 human lifetimes away struggle to attract any. The flyby is not just physically easier, it is institutionally easier. There is also a strategic point. A first interstellar mission, even a flyby, produces something no previous mission has ever produced: data from another star system. The images of a planet around Alpha Centauri, taken from inside the system, even from a single fast pass, would be the first such images in human history. The science from that pass would be enormous, even if it is compressed. The political and cultural weight of being the first society to see another star system up close is significant. A program that promises that result in 20 years has a story to tell. A program that promises it in 95 years has to compete with whatever the next 20 years produce in other fields. And history suggests that competition is not gentle. There is also the multi-shot path. A program that successfully flies one flyby probe can in principle fly more. A Starshot-class architecture allows for many probes launched in succession, each into a different geometry, each carrying a different instrument set. The cumulative science from a fleet of flybys could over time approach the science of a single orbiter with the advantage that the data starts arriving sooner. That is not a free trade. Each probe still costs a substantial laser firing, each one still spends 20 years in cruise, and the cumulative budget is not small. But it offers a path forward that does not require waiting a century for the arrival mission. The flyby strategy is not only first, it is also incrementally extensible. Public discussion already reflects this. When someone on a forum raises the question of when humans will get an Alpha Centauri probe, the conversation collapses with surprising speed toward the stopping question, the survivability question, and the human versus probe question. The most concise summary of the Starshot project that keeps appearing is, this particular mission is a flyby, so no stopping. The public language is not scientific evidence. It is, however, a useful signal that thoughtful people are already arriving at the same constraint by intuition. The stopping objection is not artificial. It is the public catching up with the physics. It is also worth being careful with what public discussion can and cannot prove. People intuitively reaching for the stopping objection is evidence that the framing is honest. It is not evidence that the mission feasibility numbers are correct. Public language can be right about the qualitative pattern, without being right about any specific quantitative claim. The literature does the second part. Public intuition helpfully confirms the first part. The two together suggest that saying the first interstellar success is most likely a flyby, and that calling it arrival would be a cultural decision rather than a physical one is on stable ground. There is also a careful boundary to preserve. Likely a flyby is not the same as stopping is forbidden. The literature does not say arrival is impossible. It says arrival is much slower, much more demanding, much more dependent on destination behavior, and much more difficult to scale. A program that picks arrival is making a choice that imposes real costs. A program that picks flyby is also making a choice, and that choice imposes the cost of accepting a different kind of mission. The first program to choose is most likely to choose flyby. The next ones might choose differently. Neither choice closes off the other. It also matters that the forecast can be wrong in only specific ways, not in any direction. The arrival mission could become more plausible if a new propulsion concept emerges that changes the mass versus speed trade. It could become more plausible if a new sail material or a new braking concept produces a fundamentally cheaper destination capture. It could become more plausible if a programmatic decision is made by a society that values arrival over speed and is willing to fund a much longer mission to get it. None of those are physical impossibilities. All of them require something that does not currently exist. The forecast is bounded by what currently exists, and within those bounds it points clearly toward Flyby First. The flyby is not the only mission that can ever happen. It is the most likely first mission, given the architectures the literature has actually worked out and the timescales those architectures imply. You can also see the forecast in how funding bodies talk about interstellar work. The Breakthrough Initiative funds Starshot specifically because it has a credible architecture and a working career timeline. NASA's NIASE program has supported several interstellar concepts at the conceptual study level, including deceleration studies, and the agency's interstellar roadmap acknowledges both the appeal of the directed energy lane and the difficulty of the arrival problem. The pattern in the funding is not a conspiracy against arrival. It is the institutions following the architectures that close. If an arrival concept closed numerically within a working career timeline, programs would fund it. None has closed in that way yet, so the funding goes to the flyby. The arrival waits for an architecture that nobody has yet drawn. The forecast that lands at the end of all this is bounded. The first starship probably reaches another star sooner by giving up the hope of stopping there. The first arrival, if it ever comes later, with a different mission on a different timeline, after the field has learned what the first flyby could teach. That is not the dramatic answer the title might encourage. It is the answer the evidence supports. The film does not need a stronger claim. The bounded one is already enough. Return to the small craft entering Alpha Centauri at 0. 2C, one last time, to see what would have to change for it to be the kind of mission that stops. The first thing it would need is permission to slow down. That permission costs either propellant on board, structure for a passive brake, or environmental help at the destination. Earlier sections walked through how each of those is paid for, so a different mission has to choose a different bargain. The cleanest sketches in the literature are honest about what each bargain looks like. The most direct bargain is more time. The Heller and Hipke bound orbit case takes the same kind of sail and the same kind of laser launch and accepts a much lower injection speed. The result is a craft that arrives at Alpha Centauri in about 95 years, much slower than the flyby, but able to enter a bound orbit using only the destination starlight. The Heller, Hipke and Curvella photogravitational case improves that to about 75 years for the same kind of sail. Both numbers say the same thing in different ways. Arrival, in the existing literature, costs at least 75 years and more typically about a century for the first attempt. The price is not impossible. The price is also not small. A second bargain is more mass. The Parakis and Hine hybrid magnetic and electric sail concept can decelerate a multi-ton spacecraft from a moderate cruise speed using propellantless braking. The mission is no longer gram scale. It is several tons, with a multi-decade braking phase and an architecture that grows as the speed increases. Groza's magnetic sail scaling makes the price clearer. High-speed braking missions to Proxima end up at hundreds to thousands of tons. None of these are unreasonable in principle. All of them are far outside the launch architecture that the gram-scale probe lives inside. A different launch system is required. That launch system does not yet exist. A third bargain is destination help. The Forgan, Heller, and Hipke photogravimagnetic concept takes the existing photon sail bargain and adds a clever use of the destination magnetic field. With the right charge on the sail and the right approach geometry, the destination star can help brake the spacecraft. That is the most elegant of the published options. It is also the most fragile, because it depends on the destination's magnetic structure behaving in a particular way during the encounter, and on the spacecraft's charge being well controlled. Garafo's results on Proxima's space weather make it clear that the destination is not always cooperative. The bargain works when the destination is in a quiet mood. It fails when the destination is in an active one. A fourth bargain is external infrastructure. None of the published concepts assume any infrastructure at the destination. Every brake is built into the spacecraft or scavenged from natural environments. A different generation of mission might assume that some kind of destination infrastructure has been put in place ahead of the arrival. That is a multi-mission program with a different shape. Small probes go first, lay down something useful, and a later, larger mission arrives with help waiting. That is not currently planned by anyone with funding. It is a possible architecture for a different century. If it ever appears, it would change the answer. it has not appeared. A fifth bargain is patience, a program that gives up on a fast first arrival and accepts a slow first arrival, can use much heavier propellantless brakes and arrive at modest speeds. A few percent of light speed gives enough kinetic energy to be dramatic compared with chemical rockets, and not so much as to make braking unmanageable. The first arrival might take centuries, not decades. The mission would not be photographed by the people who launched it. The science would arrive at a society that had moved on. That is not impossible either. It is, however, a different kind of program than any in the present propulsion roadmap, and any society willing to fund it is making an unusual long-term commitment. A sixth bargain, the one that lives at the edge of present physics, is propulsion that does not exist yet. The published roadmaps make a small space for the possibility of breakthroughs in advanced propulsion that could change the mass and time budgets. None of those breakthroughs are demonstrated, none are in flight test, or even in laboratory prototype at relevant scale. They are theoretical possibilities to be honest about, not budgeted hardware. A future field effect drive, a new family of propellantless thrust mechanisms, a refined understanding of how spacecraft might interact with the vacuum. Any of these could in principle move the trade. None of them currently does. The arrival problem, as of today, lives entirely inside the bargains the existing literature describes. So the answer the title points toward turns out to be specific and tractable. The first starship may never stop, not because stopping is forbidden, but because the first winner is unlikely to pay that price. The price of stopping, in present physics, is time, mass, destination help, infrastructure, patience, or hypothetical propulsion. The first program to fund an interstellar mission is unlikely to choose any of those prices when a much faster, smaller, cheaper architecture is on the table that delivers data within a working career. The flyby will be celebrated, the arrival will wait. The mission designers themselves, in their published papers, are aware of all of this. The Heller and Hipke work is explicit that the bound orbit case is a different mission than the flyby. The Lubin roadmap is explicit that the directed energy lane is best suited to small payloads. The Groh and Parakishein and Forgan papers all acknowledge their own boundaries. The literature is not promising arrival in the next decade. It is mapping what arrival would require and showing that those requirements are real but heavy. The field is being honest with itself. The popular conversation has not always heard the honesty, because the popular conversation likes a tidy "we are going to the stars" story. The field's story is more careful and, in some ways, more interesting. There is also one quieter point about how scientific stories change over time. Every prediction in this film is a snapshot of present physics. None of these papers are eternal. New techniques in directed energy, new materials for sails, new ideas about braking concepts, new measurements of the interstellar medium and the destination stars will all reshape the picture. The next 30 years of work on this problem will shift some numbers, retire some assumptions, and open some new bargains. What is unlikely to change is the basic shape of the trade. Stopping at another star is a second mission hidden inside the first. The cost is paid somewhere. The literature will keep finding new ways to draw the bill. It also matters that some of the bargains are easier to imagine improving than others. Patience is a programmatic choice. Mass scaling depends on infrastructure that does not yet exist, but could in principle be built. Destination help depends on remote sensing precision that is a matter of better instruments and more years of observation. Hypothetical propulsion is much harder. New physics is not currently delivered. The patience bargain and the mass bargain are bargains a society can choose to make. The propulsion bargain is not. So the most likely paths to first arrival involve some combination of the first three, and none of them will be quick. There is also a quiet correction to make about how the present arrival concepts read in popular accounts. Some popular write-ups present the bound orbit photon sail work as if it were a near-arrival proposal alongside Starshot. The Heller and Hipke paper does not say that. It says the bound orbit case is possible if the launch speed is dropped by a factor of 4 or 5 and the mission accepts a much longer trip. The popular interpretation tends to skip the speed reduction, focus on the word arrival, and present the concept as a solution to the stopping problem in roughly the Starshot timeframe. The literature is more careful than the summary, so if a first interstellar mission flies in this century, the strongest current evidence says it will be a fast flyby, gram scale, with no chance to stop, returning a brief but valuable measurement of another star system across a 4-year delay. If a first arrival ever follows, it will be a different mission, on a different timeline, paying one of the bargains just laid out. The two missions are not in conflict. They are the two halves of the same story, separated by the choices the field is willing to make. The first will tell us what is out there. The second, if it ever comes, will let us watch. Return one last time to the small craft entering Alpha Centauri. It is still moving at 0, 2C. The system is still passing it in hours. The cameras have done their work. The transmitter is beginning its long downlink. The craft is leaving the destination system at the same speed it entered, on a trajectory that takes it back out into interstellar space, with no engine to recover it. From the outside, this is the first interstellar mission. From inside the mission, this is the part where reaching turned out not to be arriving. The whole argument has lived inside the gap between those two ideas. Reaching is a geometric event. Arrival is a mission state. Reaching costs energy. Arrival costs energy and time, and structure and destination cooperation, and accepted risk. Reaching can be done with a gram-scale probe and a ground-based laser. Arrival, on present evidence, requires a different vehicle, a much longer mission, and a different bargain about what we want from interstellar flight. So the title is a forecast, not a verdict. The first Starship may never stop because the first program to fly an interstellar mission will almost certainly choose the architecture that delivers results within a working career. That architecture is the flyby. The arrival architecture exists in the literature. It is more demanding in time, in mass, in dependence on the destination, and in long-range planning, in ways that current programs are unlikely to choose for the first attempt. A later program might choose differently. The first one almost certainly will not. There is also, sitting underneath the arithmetic, a quieter point about what we will have to mean when we talk about going to the stars. A first interstellar mission in any near-term architecture will be something that crosses, takes pictures, and continues. The team back home will receive a beautiful set of data with no opportunity to ask the spacecraft a follow-up question. That is the first generation of interstellar exploration sized to what current physics and current programs can support. It is also worth being careful not to overpromise the next step. Magnetic sails, electric sails, photon sails, photogravitational assists, photogravomagnetic concepts, hybrid braking systems all exist on the page. Some are detailed enough to be priced, none are flight tested. Some require destination behavior we cannot yet verify. Some require materials we are still developing. Some require launch infrastructure that does not currently exist. The arrival mission is a research goal, decades from a launch pad at minimum. A fast flyby that returns the first close-up images of another planetary system, the first in-situ measurements of an extrasolar magnetic field, the first direct sampling of the interstellar medium across multiple light-years of travel would be one of the largest scientific events in human history. It would be brief. It would be incomplete by the standards of an orbital mission. It would still be irreversible. The geometry the mission cannot extend is the geometry the mission gets to claim first. The phrase "may never stop" then settles into a more careful form. It is not a prediction that human beings will be unable to slow their probes down forever. It is a present tense forecast about the first successful interstellar mission. Under the launch architectures that are physically serious right now, the braking concepts the literature has worked out, the destination conditions the science has mapped, and the program funding shapes current institutions actually support, the first ship to cross interstellar space is the ship that does not stop. The first ship that does stop, if it comes later. Reaching is not arriving. The first Starship may never stop. The first arrival, when it comes, will be a different mission than the one we are currently planning. The flyby teaches the arrival what to plan for.